So we finally finished second order differential ODE in homogeneous form in my textbook. Took me a while, but we got it done. Um, I don't think I'm going to change much more, even if I go next year and just look back at it and just say, what do I need to fix? I don't think there'll be much to change, hopefully. I hope. Um, so the first thing you see is a guess over here. Why this is a good guess is because of it. Um, First of all, it gives you two solutions if you think about it. Yeah. Sorry, it gives you three cases. I already messed up. It doesn't matter. I'm just going to keep on recording. It's my third time recording this. I'm not going to record again. All right. So what does that mean? There's three. For second order ODE, there needs to be two solutions. Okay. So what does e to the square root of Rx bring? Well, with the Euler's formula, you can get cosine and sine. Beautiful. With um itself being itself, you can go cosine h because cosine h is basically just e to the something, just getting rid of the imaginary. And then third, you can get a linear line. How in the world do you get a linear line here? Well, I mean, it's a little bit more convoluted than anything else. But if two roots are repeating, and for some reason, R is a real number, and I would recommend it has to be a real number. If R equals zero, then you realize this is possible. This is the solution of case one. But if this is zero, then this goes away, and this is a linear line. So in that instance, we created a linear line. We created exponential growth and decay with e to something, and then we created cosine oscillatory movement with damping. We how did and then that's why it's a good choice. It's only good for linear, but later on it's gonna be bad for non-linear. You'll see. Anyways, over here as you can see, we have case two where we have two real roots and we get this. Later on, we'll prove this one a little bit more with the massive spring. Just so you know, so it's not the final time you're going to see that. Anyway, you get this. And now you can why you can add up is because it's linear and second order. So a linear equation in linear order, you can always add solutions to a linear equations. Yes, that's always true. Never forget that. Now, do I like it? Do I understand it? Kind of. Now, why I get it is because if this is zero, then this is possible, and you can see all solutions of that. Now, because of addition, what happens is that if this is some kind of solution, if this is zero, then you can see this is a whole solution. But why does a superposition work? It's due to if you plug this back in to the original ODE, you'll find that you create two separate ODEs that are same format. Yes. But do I care about that? Maybe. Maybe we'll do a linearity test, but that is more of next book. Because linearity test is like the next book. It's like MA 105. That's the first time I learned that shit. So yeah. Um, which I think we should have learned it in 20 in differential calculus a little bit, but Hmm. maybe I should put it here then. I don't know. I'll decide. Anyways, another thing that's important is explaining Euler's identity. If you get this out, you find this to be true. How did I find that to be true? Well, this imaginary creates a cosine and sine, so you get imaginary over here too. Now, why does this imaginary go away? You'll find out soon. So it doesn't really go away. It's just that there's another constant attached to it. And now this two constants, wait, oh right, we expanded. All right, there's two of them, so they expanded. And these two over here can go together to create this group, and these two over here can create this group. It's just a simple logical diagram. What does that do? That creates two constants. And why that I goes in is because I is basically a number. and that creates a C2. Now, this is the reasoning why there's two constants, and you can see that they're not the same because you're getting two separate constants originally and adding it together, and two separate constants that, yeah, are minus. Now, you can say that there's a relationship between these two, but clearly they're two separate numbers because of the amount of constants there are. So, yeah, if we move on over here, we're going to start with a basic ODE that everyone should kind of know. I mean, because it's analogous to many other stuff, which vibration is mostly what I'm thinking about. The huge section of vibration that's is not taught sometimes. It's very important. Anyways, with this box over here, we can say, because this is the math part, I don't really talk about how I got this, all the force diagrams, all the summation and the dynamics of that. I just give you the ODE in the total form, basically. I don't really explain it. I just go for it because this is an ODE class. Now, how to solve this? Now you have to guess this, and you guess this and put it into here. Now, you see that A over here. This A is a little weird. You'll see why it's a little weird. You get this for in the right side, which gives you this in the end, and the left side you get this. So when you put this over here, A goes away because A cancels with this. Put this over here, and you get E to get away, and you get R equals to this format over here. And this is a negative. This is imaginary because this is the definition of imaginary, which is square root of -1. And you pull it out to get this format. So there we can use Euler's. And now here, why is A not the same as C1 and C2? That's a good question. But it's all about going back to the original format over here. Now we think over here that there is only one but there's a one solution, but there's a plus and minus over here. So what's happening here? And maybe I should have illuminated here, but I am just doing, let me just do omega because it's easier. So omega equals square root of k divided by m. Anyways, over here, there's this thing over here happening. We can just do -I square root of omega t. So clearly, these constants will not be the same as a, because we have two different numbers that's going to use Euler's formula to get two different constants, and you're just going to have to formulate all that. So definitely, there's a relationship between those two, but there is no, it's not the same thing as just A. Anyways, we'll move on, and now we're putting in damping. Now I'm not going to explain the math on this yet, and the physics on this yet. That is in the physics section. We're moving this over here to one side most of the time. But it looks like I didn't do that first. It's fine. We do a guess over here. Okay, why did I not move this to one side? That's a good question. You should always do that. That's normal formatting. I have no excuse for that. I'm just a dumbass. Okay, okay, I'll fix that. Should I fix that now? Probably should. Okay. What I do is basically okay, here we go. Insert. I mean, sometimes I use overleaf. A lot of times I do actually overleaf, but that's only for cases that have matrices because matrices are actually easier to do in overleaf than I can ever do here. If I do it here, everything would be like wrong and it wouldn't, I mean, it would look wrong and I wouldn't like it and it wouldn't look clean. That's why I deleted most of the, what do they call it again? Most of the linear algebra. Secretly, I just didn't like it, so I just got rid of it, and I'm adding it to the this form and this what's again this section. To be fair, there's not much to learn in the way I learned it in my linear algebra class. Basically, they taught me like the basics, but it's all memorization in my opinion. There wasn't any new content that I could think of that I could say, oh yeah, I learned something like groundbreaking. Oh, I keep on hitting that. Okay. There you go. Looks clean. All right, and now I can just delete this and just do, oh, that's not supposed to happen. So again, I use the guess the E. Now, is there any other way to get the solution without guessing? AER? No, I don't know actually. This is the way I have always been using it. Always been, I like this method. It's the easiest method in my opinion. There might be an easier way, but anyways, we get this, yeah. I also need to make sure it looks separate. I keep on not doing the right thing. For now, I'll just bold it. It looks diff, I hate it. It doesn't look correct. In this case, I just do this and call it a day because it's a new box and it looks good. Okay, it looks awful. Okay, that looks better. Yeah, that looks better. If it doesn't look good, just tell me, I'll fix it. Anyway, so we get this format here. It's all positive. This is a format that everyone likes. Everyone should do that format. Um, Anyways, we move on over here. We see that we do the same square root method. And there, again, there's three cases. Over here, I finally explained myself a little bit. Now, when you get this format over here, you see that you could, what's the right word? Do some manipulation of y. Let's just say that. So we see here, if we go back over here, that this R simplification came from this thing over here where we take a derivative. Now imagine if I went to the original format over here. So original format is including that. What's happening here is that we're losing information from the original formula to the guess we gave. So what's the information we lost is that if you take this back and change this to d divided by dt plus a plus I think it was a was it a yeah multiplied by y squared is what I did. So what I did was reformat everything to go back to this place over here. Why can we can always go back because this is always your definition. We're just adding new information that we know that this turns to this format, okay? So what does that do for us? Is that we realize we can make another guess. Because in the end of the day, how we figure out ERT was a guess. It was just a big guess, like ERT. Um, there probably is like a big formal proof of it, to figure out why you would use that guess as a good guess, but yeah. I mean it's a good guess because the derivative itself is itself, so you're redefining the derivative, but and I'm not about to look. I mean, I always go look for proofs. I should probably find that proof actually. Oh my God, I'm making myself go look for a proof for 5 hours probably. There's a bunch of proofs here that took forever to find, and I'm gonna have to go look for it. Oh God. The thing is, I love finding proofs and I love doing proofs, but some proofs are just impractical. Like the epsilon delta proof, complete useless. I don't actually maybe it has actually one use. Yeah, it has the use of proving something. Actually, I take it back. Anyways, we just guessed this time, and then like this, let's just get this over here, and we get this to be this. Now that's when you're taking the first derivative. You remember, there's a derivative square, so you do that again, and you realize that equals zero. Now, why is that powerful? Is because this should equal zero because what we where's the claim over here? Oh, over here. We claim over here that we move it to one side, so it must equal zero. Therefore, This is correct and possible solution. Therefore, that's the second solution. Yes. I wonder how long it took for people to figure this part. I don't know. Anyway, the other two is actually self-explanatory because we have done it multiple times. I don't think we need to go for. I think that we went to enough detailed explanation of the second two. Now we go and do some of these plus ODEs basically. These all have positive, positive, positive. Now, this also indicates that if it was all negative, 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 it's the same solution because you can multiply everything by -1 because this equals 0. So what that tells you is that if you get somehow get negative all constants, you can just do negative you can just do the positive version. They'll give you the same solution basically. Now I will say this. I will say this. It's very hard to find it in normal mechanics to find a negative, negative, negative. I don't think there is any. But because it's all F equal ME, MA. But you can find it in electricity. Why? It's a pain in the. It's very much a pain. But I looked at it once. It's like has an amplifier. I think it has a resistor here. Oh God, I'm gonna butcher this so badly. Something like this, I believe, and has something like this. Am I doing it correct? I'm doing it off of memory, so I might be wrong. Bleh. This is why I don't do electricity too much, but I will do a lot of electricity. But it's something like this, something, and it's a very hard convert. It's like an NIC converter, you call it. So that's called the impedance converter to negative, and then you can do the resistor version, and then so on, so on, so on, so on, so on. It is a pain, but you can finally get it, and I don't recommend doing it. Because I mean, unless you're an electrical engineer, then you need to know it. But I'm not an electrical engineer. That's why, or but now thinking about it, maybe you should. Maybe I should prove that and do it. I'm convincing myself to do it. I'm like, okay, looks like I'm gonna do it. All right, I'm gonna one day figure that out. Oh well, or I can make my electrical engineer friend spit out the secrets. Hmm. I have one electrical engineer that's probably smart enough to actually know all this stuff. I'm looking at my phone right now. Should I call him and ask him? Maybe I should. Maybe I should. Definitely should. I think I should. Well, not right now. It's too late right now. It's like 2 o'clock. Why would I care? That would be a jerk move to follow right now. Anyways, we move on to another one. This one is oscillatory, which means it's moving up and down. And we finally move it to electrical. Now, we start with charges. Yes. So charges and direct sense of the electricity is just a charge derivative. So we get this format over here where we have a resistor and Laplace. You know what? I wonder why I made this question. Well, oh, yeah, because I wanted to solve something like this. Yes. Uh, uh, yes, I wanted to solve something like this. So this is a solution that you do not need to do some e to the r thing. You just have to take an integral of it, and you can see over here what I mean. You take an integral, 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 because there's no q over here. That makes it hard. Now this is more intuitive. This solution is like way too intuitive because you're making it first order over here. And this actually is a solution for I, if you didn't know I, and then this is but it doesn't matter. You don't need to know that. Anyways, you get that thing and you just do a first order ODE basically and get go to sections 4.7 to you get that and you solve this. That's it. That's not bad, right? And unfortunately, the ODE is kind of lackluster a solution because it's just a line. What that means is that I don't think there's a use for this. It's like a solution, and I mean, the reason I brought this up is because I know a question in real life that uses this, but um, but for a different case. But that case is so hard to understand that you it won't be worth it to teach you right now. So I decided to do it this form, but I don't think this ODE has any use other than it exists. I don't think. Next one. Okay, these are going to be deleted. Why are they going to be deleted? These two are kind of useless. They're sitting ducks with no uses. Why I say that is because you're you're gonna get initial condition current and a derivative. Okay. Yeah, you could do this, but yeah, I mean, we have done this kind of ODE before. We know this already. So I'm gonna save some space in my textbook and just clobber it. Oh, I was I was thinking about this for a long time, and I will delete this again. So, uh, what that means is I'll come down. Let me go down there. Why I'm deleting it is that it's all positive ODE, and we've done that multiple times. And I realize there's no reason for me to keep these, so we're gonna get rid of them. So much time wasted, so much time wasted. It breaks my heart, but it needed to go, because it was holding my book back. There's no use for it. It's an ODE chapter. We don't need it. Now, this one is definitely more needed. Um, okay, oh yes, because of how I solved it. This solution has uh two different types of what's they called again? Oh my God. Initial condition. You have a voltage initial condition and a current initial condition. These are two different types of conditions, so we can't just rely on this. We can't rely on this. We need another ODE. So we're going back to add all the voltages in. This is adding all the voltages like, wait, did I do this correctly? Okay, I did this wrong. This is correct, but this is for, yeah, okay. This is the derivative of the current. Of the voltage, sorry. A derivative of the voltage. Yeah, this is not needed. Sorry about that. I am fumbling here. I'm fumbling bad here. Oh, by the way, at this point, you should know all the con I think I talked about the uh assumptions already, so I don't need to talk more about that. I won't do it. I won't bore you more with uselessness. I can't believe I made that mistake. Anyways, this you need to be a little bit more smart, a little smarter, where you have to realize this is true. This IC, the second one, can be solved by the capacitor and dV/dt, which allows you to get this format over here, which tells you that the derivative of voltage is also zero. Oh, you did need the voltage one, so you this thing. Oh, I'm stupid. I needed that back. Oh God. Do I have the original version? Okay, I was wrong. I needed that. I guess I'm gonna rewrite it. I was right the first time. Oh God. Uh, okay. Okay, notice that well, I'm angry at myself now. I'm wasting my time. That the battery um is no longer available available Little. I spelled that horribly wrong. Luckily, there's always corrections in this variable. So um capacitor can take its place because um capacitor holds charges temporarily. Oh my God. Yeah, I fumbled so badly in here. I fumbled two times. Two. I knew I was right the first time, and I thought I was wrong, and now I'm paying the price of being dumb. It cost a lot to be dumb. Um. Okay, that looks good. Okay, notice that battery is no longer a variable. Um. Uh. Do you understand why? It's because of ice. Because of switch. If you didn't know, it's because of switch. Maybe that would be a better explanation. Yeah. Oh my God. I knew the answer and I fumbled hard on it because I got it right the first time and I changed I thought I was wrong. Oh my God. It's so stupid sometimes. Oh, oh, what happened here? Oh, I see what keep on making mistakes. There's a reason why I kept it there. It's because of that damn compressor. Well, I'm gonna change it a little bit. And then we're gonna do a sneaky trick because I want it to look clean. We're gonna change that to here. I'm gonna actually order this to the back, and then we're gonna make it look like this, and we're gonna actually move this over here. Man, I knew that. I can't believe I fumbled badly. I I'm more angry at myself than anything else, honestly. To the Well, it's already to the back. Why is it happening? Oh, because this thing's just fill it up with white and it should be good. Uh, okay. Switch off because as you can see I'm sleepy also because of the switch. Right, and I realized I just did a long sentence. So kept capacitor can take its place because capacitor. Okay, so that's good. That is solved. Oh my God. So we have here why is it called cur oh, we're trying to find current. Um, Another ODE is needed. Obviously, this is true. Another ODE is definitely needed there. And this is a basic electrical engineer question. One of the more basic ones, because I think it's one of the more basic ones. Don't remember if it is. I'll have a whole section on this kind of stuff later on in the next book. Um, Over here we have this. We're definitely dealing with case three. I gave you the solution, and this makes sense because it's a capacitor. So think about capacitor, it's always temporary, so it's not permanent. It's never gonna be permanent energy. Um, so it's always going to flow down to zero with capacitors. Now with battery on the other hand, you're gonna assume that it keeps on giving energy, which is why it's gonna explode. That's why it's gonna be a negative one way or another. That kind of question is actually a little bit more difficult because that's a inhomogeneous equation. Actually, it's not gonna be infinite. It's just gonna let me think about this. I can't remember. I need to go to sleep. I was gonna stabilize like this. Just gonna go over here. All right. I'm gonna now clear up and then just move on because I'm talking to myself like a crazy maniac and I need to keep on going. I need to get myself Check on this. Oh yeah, this is because I never explained to you how to solve one of these, um, which I gave over here. Okay. So it seems like I never did the viscosity with pendulums. That's fine. I'm gonna do that in the physics section, so we're all good. We're good. We're good. Um, yes. Okay. So over here we definitely have ODE. We solved it, and I gave you a solution that has basically it's still not possible in real life, but has a constant unless you use controls, constant oscillation. I realized I never gave you that question, so this is the ideal pendulum. I gave it to you now, so wonderful. Now this is valid for 15 degrees, so do that what you will. And it has to be infinite, so it has to be a perfect pendulum, so it's not realistic. Now, the first real question about another negative is an inverted pendulum. We'll have a negative over here. Now, this is the first one that has, actually, it's the second one? It's the first one, right? First one that has a negative constant when you put it all on one side and keep a zero on the other one. Why are we doing this? Why are we doing all one side positive and one no sorry, one side all um you know variables and one side always zero. Now we're not tr to be clear, it's not always. Now the thing is over here, what I'm fumbling here. I'm telling you a lot of things and I'm not explaining. Um, so what I'm trying to say is over here we have available data. We have available data, and that's the reason why we want to segregate them. Sounds wrong. Anyways, we want to keep this over here so we can actually formulate this like force, like a not force, but some active component like a machine claw moving it back or making it go and initiating or something like that. Now, isn't it the initial conditions and other stuff initiating? Yes, but there could be like a constant rotary motion with it that cannot be shown over here, like a motor or something, and that goes in this side. You see that with inhomogeneous, which is 6.6, I believe. We're not there yet. We will get there, and I will make a question on it. And that will be painful because the solutions for that, yeah, there's many ways to solve it. One is matching coefficient. The other one is variables, and then there is the Fourier's transformation, and there's a Laplace transformation, and all of those will be explained. I will have to relearn some of them. Fourier's transformation. I need to learn Fourier's transformation again. Um, Laplace transformation is just a table. Am I forgetting anything? I hope I'm not. I probably am, but I can't think of it. Anyways, we're moving on here. You all that? Yeah, this is correct. Uh, And then first nonlinear. So here's the thing. I wanted to put one nonlinear question here, and the pendulum just gave me a great opportunity to put one. Now this is second order nonlinear, the negative. Oh, by the way, I wasn't done explaining the first one. Um, you can imagine the first one over here. It's gonna explode to infinity because there's a negative over here. The reason why negative is so hard to manage is because it'll blast off and she'll always pretty much break if it was a physical system. So imagine an explosion, gunpowder, some kind of PODE that has some kind of pendulum that breaks and breaks off. That is what inverted pendulum is because this will try to go down, it'll flop over here, but it won't try to go back up because it hit the ground. Um, Now, technically speaking, this ODE could have, in theory, done this and done this and done this and done this. Will this ODE show this? No. This is gonna explode. That's why it's only valid for 15 degrees over here. Now, the ODE that will show this is the nonlinear version. Now, because of this wall over here, I made it crash. But with this ODE, you can theoretically make it go like this, like this, like this, like this, all you want. And I don't want to do it because I mean, you can, but there's no point to do it. I showed you over here. Now, this is the first one that has a different way to solve it, mainly due to it being a not an ordinary linear ODE. This is like a nonlinear. Anyway, the first thing you have to learn is this chain rule process. So the derivative of this is equal to each other. Why? How? How can this be equal? Well, think about what the chain rule does. Now, if I took this variable over here and said that this thing over here, and I just said this equal x over here, and we did dx squared divided by dt, well, you realize that so this is I'll put t over here. We put t over here. We need to make this work. Uh, we'll put actually that was right. Why would I change that? All right, so x over here dt. Now you realize that dx square dx over here dt is the same thing over here. Did I do that right? Yes, dx. Now this over here, you'll realize is 2x. And you'll see dx over here and dt. And you'll substitute this over here, which is why I did something wrong. Oh, this cancels out, and then this is 2x, and then, yeah, whatever. No, this doesn't cancel out. This is right. This is right, yeah. This is 2 theta dot, and then this is uh, d squared dt, which is theta double dot. Which is shown over here. And that's how this one works. Maybe I should have shown that before, but same process for the sign and the data dot. You just do that again and again and again. Ultimately, then it's just algebra and some integrals. Just so you know, this integral is like this. This is why you get a plus c over here if you didn't realize that. Yeah. Anyway, this shows you this format over here. And this, if you let it go, we'll do this. Oh no, that's the wrong one. I meant this one. I think it's actually like something like this, but yes. So what I'm trying to say is that you can show a full 360 without crashing a wall, but because of simplicity, I made it crash the wall. So the simulation crashes to a wall because I didn't want to deal with that shenanigans. Um, over here, because it's harder to explain, then it's just gonna crash. Over here, we bring in the another negative. This time a negative like this. So this can also mutter another type of ODE that can be negative a dx dt square. Oh my God, it's so hard to write this thing all out. Plus b dx dt and then minus the CX. Why I'm showing you that is because if you show that ODE, because if you're taking an ODE class, what will happen is that there's not going to put any. A lot of times they don't put the physics in; they just show you a lot of ODEs and show you how to solve it. So if that happens, you know you got this one. It's the same. You can make it into this form and solve it. There you go. And in my class, it was basically that a lot of theoretical non things without any physical meaning. Luckily, yeah, but it makes sense. It was a math department, so just not gonna do that. And he wasn't a physicist, physics person or and practical person, so he would put that in the homework. Anyways, there's three cases again, and then you see the uh a few more of these things. So it's the same process, it's the same thing. Um, yeah. Oh, did I explain how you get this? You basically get this general formula over here and you plug x equals 0. So this is 0 over here and 0 over here. And you see the t's, all the t's go to 0 and you see C1 equals 0 basically. And you do that for the other ones and so on and so on. Some of them become systems. I wonder if I gave a system question. Probably did. Here's the first one that has negative over here, but there's a plus over here. That's the viscosity trying to dampening the velocity of it. But at the end of the day, it will fail, as seen by this over here. Oh, here's the first system question. Is it system? Yes, because there's a system over here, which is just you're gonna have to solve this linear algebra, which that's such a simple linear algebra. Never mind, it's not really. Anyways, you explode over here. Yeah. The reason I didn't give you hard IC is because there's no point. I can give you 10 over here and 5 over here, but what's the point? There's no point to it, so I decided not against it. I mean, the hardest one I can do is data 1 and 1, but what's the point? First of all, why would your data be like 1? And why would your velocity like this? Like, why? I mean, yeah, I mean, it makes whatever. Anyway, I also said it's to stop at 15 degrees because after that, it is nonlinear. So you're going to have to do that equation I showed you earlier with the sine h and all the weird stuff. Um, um, over here, I showed you it before. Over here with all the cosine, sine, word stuff. Yeah. Anyways, you get the final solution. Oh, by the way, this is a more general version of inverted pendulum with weird masses. Anyway, here's the one that I will not show you the circuit for because circuit will just confuse the hell out of you. I'll just give you the ODE and you solve it. And here's the ODE and you solve it. With this said, I think we went through every single type of ODE possible that's linear and second order. And that's the whole purpose of this. We went through all of it. Now I'm going to stop here because I don't need to go anymore. It took forever, but we went through all the negative possibilities because this can be a positive, positive, and negative. Yeah. I didn't want to do a circus, man. I didn't want to put circus in the last one because it's, gonna be a lot. I knew it was gonna be a big circuit and I couldn't show it without confusing everyone. So instead, I chose to I looked everywhere for a different type of ODE that would work with this. I looked everywhere, could not find a single one. So there you go. That's my final say there. I had to use this. Anyways, next is Wolskian and the rotation matrix, which in my opinion, the rotation matrix is what I'm going to focus on because the next section with the variable parts, we're going to do Wolskian all the time because the bottom can be, actually, we're going to just do it once and then move on to Laplace because there's no point in doing this like 5 times. Anyways, we're also going to delete this. We don't need to do that. Um, wow, these look bad. I'm going to have to fix this and make it look good. That's definitely something I will have to do. Oh, the plus tables. I'm gonna have to do is prove every single last one of these because I don't like how I did this. Um, yeah, okay. I also don't like this, so why did I do it that way? Anyways, wish me luck. I'm gonna have to do it. Anyways, I'm gonna stop my recording here.